we will use the definition of derivative to compute slopes of tangent lines. Let's begin with f of x equals x squared minus 4x plus 1. We wish to find f prime of 1. The definition tells us that f prime of 1 is the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. Let's plug the relevant things into the numerator and see if we can simplify. We have the limit as h approaches 0 of 1 plus h squared. And notice that the 1 plus h is getting plugged in for x in parentheses. Minus 4 times 1 plus h plus 1. Next we need to find f of 1. Plugging 1 into our original function gives us 1 minus 4 plus 1, which is minus 2. But remember, we're looking at minus f of 1 in the numerator, so we get minus negative 2. Now this is all over h. Let's multiply out the numerator and see if we can find more simplification. 1 plus h squared is 1 plus 2h plus h squared. Now distributing the minus 4 gives us minus 4 minus 4h. And finally, 1 minus negative 2 is the same thing as 1 plus 2, which is plus 3, all divided by h. Now let's take a moment to make sure we saw where all of this came from. The 1 plus h in parentheses squared is now 1 plus 2h plus 4h squared. The minus 4 times 1 plus h is now minus 4 minus 4h. And the plus 1 minus negative 2 is now the plus 3. Let's see if we get more simplification when we combine like terms. We have the limit as h approaches 0 of, well, let's first look at our constants. We have 1 minus 4, which is minus 3, plus 3. Those all cancel. Next we have 2h minus 4h, which gives us minus 2h. And finally, the only term that's left is plus h squared. Plus h squared. And this is still all over h. Much simpler. In fact, we now see that there is an h in each term in the numerator. We can factor it out. So we have the limit as h approaches 0 of h times minus 2 plus h over h. And now that the h is factored out of the numerator, we can cancel with the h in the denominator. Remember, you can only cancel things out of both the numerator and the denominator once they're factored out. If there's not another term, like in the denominator, it's implied that there is a 1 left behind. We're left with the limit as h approaches 0 of minus 2 plus h. As h approaches 0, this approaches minus 2. Let's look at another example. Let g of x equal the square root of 3 minus x. And let's try to find g prime of minus 1. According to the definition, g prime of minus 1 is the limit as h approaches 0 of g of minus 1 plus h minus g of minus 1 over h, which is the limit as h approaches 0 of, remember, we need to plug in minus 1 plus h in for x in parentheses. We get the square root of 3 minus 1 plus h. Close the parentheses. Let's make sure our square root covers everything. Minus g of minus 1 is the square root of 3 minus 1, which is the square root of 4. We'll replace that with a 2 in the next step, all over h. Let's simplify. We have the limit as h approaches 0 of 3 minus negative 1 is the square root of 4. Now, we must distribute this minus. Minus plus h gives us minus h minus the square root of 4 is minus 2 all over h. Now, if we simply try to substitute h equals 0, in the numerator we get the square root of 4, which is 2, minus 2, which is 0, divided by h, which is approaching 0. Remember that 0 divided by 0 is an indeterminate form, and it also indicates that there are some algebraic tricks we may be able to do to find a limit. In this case, because I see a sum or a difference of two expressions involving a radical, I'm going to try multiplying the top and the bottom by the conjugate, the square root of 4 minus h plus 2. Let's multiply out the numerator. We get the limit as h approaches 0 of 4 minus h, that's the product of the first terms, the square root of 4 minus h times the square root of 4 minus h. Now, the outside and inside terms, when you multiply them out, cancel each other, because we get plus 2 times the square root of 4 minus h minus 2 times the square root of 4 minus h. The only other term that's left is the product of the last two terms, which is minus 4. The denominator we could also multiply out, but our goal is to cancel out the h in the denominator. And in order to do that, we'll need it factored out anyway, so let's leave it alone. Simplifying the numerator gives us the limit as h approaches 0 of 4 minus h minus 4. And the 4's cancel, which leaves us with minus h, which I'm going to write as h times minus 1, divided by h times the square root of 4 minus h plus 2. I'm writing it this way because now I have an h factored out of the numerator and an h factored out of the denominator, which means I can cancel. Now, as h approaches 0, the numerator is approaching minus 1, and the denominator is approaching the square root of 4 minus 0 plus 2, which is minus 1 over 2 plus 2, which is minus 1/4. Let's do one more example. Let f of x equal 1 over x plus 1, and let's find f prime of 2. The definition says f prime of 2 is the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. Substituting gives us the limit as h approaches 0 of 1 over 2 plus h in parentheses plus 1 minus f of 2, which is 1/3, all over h. As in the previous examples, as h approaches 0, the numerator is approaching 1 over 2 plus 1. This is 1/3 minus 1/3. That's 0. The denominator is approaching 0. This indeterminate form, remember, indicates that there may be some algebra we can do to simplify. Let's reevaluate what we have in the numerator by simplifying. We have the limit as h approaches 0 of 1 over h plus 3 minus 1 over 3, all divided by h. Because this expression involves fractions inside other fractions, I'm going to do what I can to eliminate those. Let's multiply by the fancy one, 3 times h plus 3. That would be the common denominator if we were going to combine these fractions. Since we're multiplying both the top and the bottom by 3 times h plus 3, we are not changing the expression. Now, let's distribute. We have the limit as h approaches 0 of 3 times h plus 3 divided by h plus 3 minus 3 times h plus 3 over 3 all over h times 3 times h plus 3. Notice that in the numerator, the expression that we're multiplying in is being multiplied into the numerators of our original fraction. Notice further that we get cancellation. What are we left with? We have the limit as h approaches 0 of 3, that's what's left of the first fraction, minus, in parentheses, h plus 3, that's all that's left of the second fraction. This is all divided by h times 3 times h plus 3. The numerator simplifies. We have the limit as h approaches 0 of, in order to do the simplification, let's distribute the minus sign. That would change that to a plus and change the signs on the inside. What we have left is 3 minus h minus 3. The 3's cancel, leaving us with minus h. This is divided by h times 3 times h plus 3. The numerator we can rewrite as -1 times h. And now that the h's are factored out of both the numerator and the denominator, we can cancel. What are we left with? The limit as h approaches 0 of -1 in the numerator, 3 times h plus 3 in the denominator. And now, as h approaches 0, the numerator, since it's constant, is simply approaching -1. The denominator is approaching 3 times 3. That gives us a limit of -1 over 9.